Assalamu alaikum. Today we will discuss the pressure and kinetic molecular theory. في المحاضرة السابقة تحدثنا عن الكاينتيك ثيوري، وبهاي المحاضرة راح نشوف علاقة البريشر مع الكاينتيك ثيوري. Also we will discuss the Dalton's law. The macroscopic phenomena of pressure can be explained in terms of the kinetic molecular theory of gases. Assume the case in which a gas molecule represented by a sphere is in a box and length L. Then we have this a box and length L. Considering the sphere is only moving in the x direction, we can examine the instance of the sphere colliding elastically with one of the wall of the box. إذا الموليكول تصطدم elastic مع الوول للبوكس. Okay. So the momentum of this collision is given by B بتساوي الماس في velocity mv. In this case, B equal mvx. Since we are only considering the x dimension, so the total momentum change for this collision is given by mvx ناقص m ناقص vx. ليش ناقص؟ لأنها عم بترتد، فراح تكون ايش؟ نيجاتيف. اذا وتساوي 2mvx. اذا دلتا بي ام راح تساوي 2mvx. Okay. Given that the amount of time it takes between collisions of the molecule with the wall is راح تساوي التايم هي عبارة بنعرف الديستانس على الفيلوسيتي، أن الديستانس اللي هو L اللي هو اللينث للبوكس على ال Vx. So we can give the frequency of collisions of the molecule against a given wall of the box per unit time as Vx over 2L. 2L ليش 2L؟ لأنه بيرجع مرتين. So we have this time as Vx over 2L. So one can now solve for the change in momentum per unit of time. 2mvx مضروبة في Vx over 2L هاي راح تساوي ايش؟ mvx square. Solving for momentum per unit time gives the force exerted by an object. نعرف انه الفورس بتساوي الماس مضروب بالاكسلريشن وتساوي المومنتم over time. So with this expression that the force equal mvx square over L, one can now solve the pressure exerted by the molecule collision where area is given as the area of one wall of the box وتساوي الاريا بتساوي L square. لكن نعرف انه البريشر بتساوي الفورس على الاريا، ولكن الفورس تساوي mvx square over L. اذا البريشر راح تساوي mvx square over L cube. So the expression can now be written in terms of the pressure associated with collision from n number of molecules. So B بتساوي nmvx square over the volume. طبعا احنا بدلنا الفوليوم اللي هي L كيوب. إذا بدل L كيوب اللي هي عبارة عن الفوليوم in this equation. So this expression can now be adjusted to account for movement in the x, y, and z direction by using mean square velocity as we see in past lecture, for 3 dimension and a large value of n. So the expression now is written as P pressure equal N في M في V mean square velocity over 3VB. Okay, so this expression now gives pressure a macroscopic equality in terms of atomic motion. The significance of the above relationship is that the pressure is proportional to the mean square velocity of molecule in a given container. Therefore, as molecular velocity increase, so does the pressure exerted on the container. We will connect the real gas between real gases and the kinetic theory. كمان مرة نراجع real gases. So real gases often don't behave like ideal gases at high pressure or low temperature. Ideal gas law assume no attraction between gas molecules. Also, gas molecules don't take up space. Based on the kinetic molecular theory, at low temperature and high pressure, these assumptions are not valid. إذن, so what is the effect of the finite volume of gas particle? At low pressure, the molar volume of argon is nearly identical to that of an ideal gas, but as pressure increases, the molar volume of argon becomes greater than that of an ideal gas. At higher pressure, the argon atoms themselves occupy a significant portion of the gas volume, making the actual volume greater than that predicted by the ideal gas law. You can see here, because real molecules take up space, the molar volume of real gas, the real molar volume of real gas is larger than predicted by the ideal gas law at high pressure. And so this is the relation between molar volume and the pressure at unit atmospheric. So this is the argon, and here is the ideal gas. Okay, so how it's modified the ideal gas equation, as we said in past lecture, Van der Waal in 1873 modified this ideal gas equation to fit the behavior of real gases at high pressure. So the molecular volume makes the real volume larger than the ideal gas law would predict. Van der Waal modified the ideal gas equation to account for molecular volume. So B is called a Van der Waal constant and is different for every gas because their molecules are different sizes. إذن these constant تعتمد على السايزز للموليكولز. So بنعرف إنه ال V ideal gas equation V في B بتساوي nRT. إذن with modified V تساوي nRT over B plus NB. At high temperature, the pressure of the gases are nearly identical to that of an ideal gas. But at low temperature, the pressure of the gases are less than that of an ideal gas. At the lower temperature, the gas atoms spend more time interacting with each other and less time colliding with the walls, making the actual pressure less than that predicted by the ideal gas law. So van der Waal modified the ideal gas equation to account for the intermolecular attractions. A is another van der Waal constant and is different for every gas because their molecules have different strength of attraction. إذن المعادلة ideal gas B pressure nRT over V. So the pressure nRT over V minus A مضروبة في N over V الكل تربيع. And here remember that the volume nRT over P and V تساوي nRT over V plus and B. This is correction of volume and this is correction of the pressure. So combining the equation to account for molecular volume and intermolecular attraction, we get the following equation used for ideal gas. B plus A over V كل تربيع مضروبة في V ناقص N B تساوي nRT لأنه B for ideal gas B في V تساوي nRT. For real gas this is become the van der Waal equation. And this terms is the correction for intermolecular forces and this term and B is correction for particle volume. Here is the table for A constants and B constants for gases. Okay, so let us to take example again. Another example, if SO2 were an ideal gas, the pressure at 00 Celsius exerted by 1 mole occupying 22.41 liter would be 180 m. Use the van der Waal equation to estimate the pressure of this volume of 1 mole SO2 at 0 Celsius. So rearrange van der Waal equation to give the pressure and substitute the value R, T, V, A, and B. So the pressure is get 0.98980 m. And we cancel these units together and we have the result is 0.98980 m. Oh, I will stop at this point and we will discuss the next lecture, the gas mixture and partial pressure or for Dalton's law of partial pressure. So thank you for your attention.